So, this is lecture number 28 of the Micro and Smart System course, and here we would be talking about the finite element method development as such, and as a part of it we will develop the finite element equations and the shape functions that are required for the development of many elements. So, just to give a summary of what we talked about in the last class, we said that finite element uses the weak form of the governing equation with the weight function v, which is same as the dependent variable function which is given in equation 1 here. So, the system under investigation is split up into many subdomains which we call it elements, and each element has a number of nodes. Over each of these subdomains, the dependent variable is assumed in certain form of a series which is given by here equation 1, where a n of t and phi n has certain meanings. Let us see what these meanings are. So, the equation is a standard form for the equation 1 is the standard form for the most of the approximate methods that were described previously. However, here in FEM each, as I said earlier, have specific meaning. For example, a n of t represents the nodal degrees of freedom, that is each element will have a node. For example, if it is a rectangular element, we have 4 nodes, and the degree of freedom in each of these nodes represents this a n of t. And the phi n of x y z represents the shape function, which is normally denoted by n in finite elements. The above variation of the dependent variable, when substituted into the weak form of the governing equation and minimized it, we get two sets of problems. If the problem is simple static, that is the variables where a n is just a function is a constant and the phi is not a function of t, then we get a set of algebraic equation which is normally for static problems. If the problem is dynamic, then we get a coupled set of ordinary differential equation. That is basically a governing differential equation is converted into algebraic equation for static problems, and a coupled set of ordinary differential, that is the PDE is transformed into a set of ODEs for dynamic problems. Let us summarize the procedure now. So, basically what it says here is the substitution of the assumed function into the weak form of the governing equation, and the subsequent minimization will give us a set of two matrices, what is called the stiffness matrix and the mass matrix. And the mass matrix will be there only if the structure is dynamic in nature, that is it is subjected to inertial laws. And the size of these matrices depends upon the number of nodes and the number of degrees of freedom that each node can support. For example, in order to explain this in little more detail, let us take a simple rod problem. Okay. So, the rod problem will basically will have 2 degrees of freedom, that is the axial displacement u1 and u2, and this is node 1 and node 2. So, in this case the stiffness matrix K, which we represent, will be 2 by 2. If the same problem is now a beam problem, that is when the loading is in the transverse direction, in this direction, then it will take 2 degrees of freedom, that is the W1 and theta 1, the slope, and W2 and theta 2 slope. So, basically in which case the stiffness matrix will be 4 by 4. The other possibility is these are all 1D elements. Suppose we have a rectangular element, then this has 4 nodes and each node can support u1 v1, then this is u2 v2, this is u3 v3 and u4 v4. This will be stiffness matrix will be 8 by 8. Suppose we have a triangular element, other possibility, then we have 3 nodes, and if each node can support 2 degrees of freedom, then the matrix K will be 6 by 6. So, basically it depends upon how many degrees of freedom it can. We will come to the definition of degrees of freedom little later. Now, the mass matrix formulated through the weak form, as I said, what we get there is called the consistent mass matrix. There are other ways of formulating the mass matrix, which we will not go in detail in this course. It is beyond the scope of this course. So, in which case if that is done, the consistent mass matrix is a completely full matrix depending upon the what structure. It is 2 by 2 for a rod, 4 by 4 for the beam, etc. However, if there are alternate ways of formulating this mass matrix, suppose you take the total mass and lump only to the translation degrees of freedom, then you will get a lumped mass matrix which will be completely diagonal. There are various advantages of using the diagonal matrix when you do a dynamic analysis, which we are not going through in this course. The damping matrix, another matrix that is coming from the weak form, is many times not used in weak form for many reasons, because damping is a very complex phenomenon which is not well understood even today, but that has to be there. The damping comes because whenever there is a time dependent force, then this force will not be sustaining in the same amplitude, it will die down after some time because of the various reasons such as the environment, such as the material in which the response is traversing, etc. But however, to represent it, they formulate the stiffness and mass matrix and take the damping matrix as a combination of the stiffness and damping stiffness and mass matrix, and such a matrix is called the proportional damping matrix. There are two categories of numerical method of solving under FEM. One is called one is based where the forces are basic unknowns. These are called the force method, which is also a kind of FEM method, but is not very popular. But the conventional FEM method, which is extensively used, is called the stiffness matrix or the stiffness method, where the dependent variable, say the displacement in the case of structures, or it is a current in terms of the current and magnetic field in terms for the Maxwell's equations or the electromagnetic problems, or the basic unknowns, and the satisfaction of the compatibility of displacement across the element boundaries is automatic as we begin here. So, in order to make this very clear, let us again take a domain, and this domain is split up into, say, a number of elements as shown here. Let us isolate here. So, in this case, the displacement coming from this element and the displacement coming from this element are compatible at these edges, because we start with the compatibility. However, because of the applied loads somewhere else, there will be forces generated, and the forces across this inter-element boundary will not be compatible, will not be in equilibrium. So, this equilibrium has to be enforced. How do we do that? So, we generate the matrices here for each of the stiffness matrix. When we assemble it, the assembly process ensures that the forces here are in equilibrium. So, basically there are two aspects which we said in the elasticity. One is the compatibility and other is the equilibrium. Here the compatibility is ensured, whereas the equilibrium has to be enforced. The assembly of matrices will give to the basically ensure that the equilibrium is satisfied. So, when we assemble the whole matrices, so in the case of a rod we have a 2 by 2, when we assemble all the matrices, say it has 10 degrees of freedom. So, the total assembled matrix will be 20 by 20. So, it will be n by n. So, if there are n degrees of freedom, so the assembled stiffness matrix will be of the order n by n. Then what we do after the assembly process, then we get a stiffness matrix, say your K will be say 20 by 20 for a 10 element rod matrix, let us say, and this 20 by 20 will correspond to the 20 degrees of freedom in the rod. Each element will have 2 degrees of freedom. There are 10 elements, so there are 20 degrees of freedom. So, in that 20 degrees of freedom, if you cannot solve it without applying the boundary condition, because this matrix will be singular. So, basically you will have your force vector F, which is 20 by 1 will be equal to k into u, which is 20 by 1. So, this will have where u will have basically u1, u2 to u20. So, out of which we need to say which of the boundary conditions are known. Suppose u1 is 0, so that has to be eliminated. So, when we eliminate it, we get a reduced stiffness matrix, and similarly we can get a reduced mass and damping matrices if we are doing a dynamic program. Okay. Then basically the reduced stiffness matrix is solved for the applied loads. So, many times the load would be basically distributed. For example, if we have a structure, say we have a rod where some portion is having some distributed loading. So, in the finite elements we can only handle concentrated load. So, basically we split this element into sub elements. So, this will be element 1, so this will be element 2, and this will be element 3. So, I will name it as 1, 2 and 3. So, each will have say 2 degrees of freedom. So, this will have node 1, 2, 3, 4. So, you will have 1, 2, 3, 4, 5, 6. So, 5 and 6 has a common node 3 in the global direction. So, now we have 2, 4, 6, 6 degrees of freedom. Okay. So, now what we do basically is this distributed load has to be converted into a concentrated load acting in these 2 element edges, and when we assemble it corresponding to the degree of freedom 2 and 3, we have the nodal vector going into the matrices. So, essentially what we are saying is that distributed load has to be transformed into equivalent concentrated load when we do a finite element procedure. So, the resulting equation will then be solved using the standard algebraic solution methods, and we solve for the displacement. Once we get the displacement, we now use the elemental equation for each element f equal to ku, then get the forces and hence the stresses, and whatever quantities you want beyond displacement can be got by post processing the results. So, as I said earlier in my earlier lectures, the finite element procedure has the pre-processing, that is meshing the system, then the solution of the equation and the post processing. So, the 3 steps have to be followed in the finite element procedure. And in the case of dynamic analysis, we have a PDE, that is a partial differential, is converted into an ordinary equation which are coupled together to many differential equations. There are various methods that we use to actually solve this equation. Such methods are called the modal methods, where we use the eigenvalues of the we convert the dynamic problem into an eigenvalue problem and find the eigenvalues and use these eigenvalues to find the dynamic response, or we can use finite difference scheme, which we talked about little later, by actually using the finite difference scheme for the ordinary differential equation in the reduced ordinary differential equation, which we call it as time marching schemes. We are not going into details of these right now. So, to understand this, we can take this big flow chart. So, this is the pre-processing part, the left hand part. So, this is the pre-processing part, where we start, we read the mesh constraints, where the loads are, what are the types of loads, what are the types of materials. Okay. Then we pre-compute all the elemental properties, and then we initiate the displacement. So, if you are doing a dynamic analysis, we can ignore this. So, we begin the do loop over the element, we find the strain displacement matrix, we find the material matrix, and if it is a nonlinear problem, we have to update the stress, we do not do about it. Then we solve for the displacement, compute the element forces, and we do this for all the elements. So, before this we generate the stiffness matrix, assemble it. After we generate the strain displacement matrix, we generate the stiffness matrix, assemble it, solve for the displacement, find the elemental forces. If we are doing a dynamic problem, we have to set the initial displacement to 0, then we need to begin a time marching scheme, then we go about doing it, apply the constraint loads, find the new displacement, and this has to be done for each of the time step. So, now let us begin the finite element equations. How do we get the finite element equations? So, we again talk about we go back and revisit our energy theorems, and one of the energy theorems we derived is the Hamilton's principle, because we are now trying to derive the equations for the general dynamic equations, and then remove the dynamic part of it and solve only for the static part. So, if you go back to our Hamilton's principle, the Hamilton's principle states that the minimization of the total energy between the time t1 and t2, that is T is the kinetic energy, U is the potential energy, and Nc is the work done by the non-conservative forces, and if you integrate this with respect to t1 and t2 equal to 0, will give us the governing equation. So, now let us go and find out each one of them. Let us take the kinetic energy for a 3-dimensional system. Kinetic energy is nothing but integral over the volume of the mass times velocity, and the velocity has three components, that is u, v, w in the 3 coordinate direction. So, we have u dot, v dot and w dot here. So, now we take this, and you know that the variational operator operates like a differential operator. So, we take the variation of in the 3 respective directions and then integrate by parts. So, now when we take the variation of t, now we have rho into du by dt into d by dt of delta u, dv by dt into d by dv delta u, etc. Now, you have 2 time dependent functions, we integrate by parts and then make sure that the first variation vanishes at time t1 and t2. We have all done this in the last class. So, I am not going to repeat it here, and when we do this, ultimately we get this region, this expression where u double dot is basically the acceleration. So, this can be written in the matrix form as variation of d transpose vector into d dot into v, where d is nothing but d double dot is nothing but a vector of acceleration, and delta d is nothing but du, dv and dw. So, we have converted this equation into matrix form with a variation on the displacement vector multiplied by the acceleration vector. Next, we take the strain energy part. We know the strain energy, we derive the strain energy for a 3D state of stress, which is nothing but is given by this expression, where it is a product of stress and strain in each of these planes, which can be written in matrix form in this form. And when we take a variation, we have to take a variation on displacement or the quantities dependent on the displacement, and the quantity dependent on displacement here is the strain, because we know the strain displacement relationship. So, we write this delta u by this form. Now, we take the work done by the non-conservative forces, which can be split up into 3 different forces, one due to body force, one due to surface force acting on the surface, and one due to damping force. So, now work done by the body force is Bx into u, By into v, and Bz into w, and it is a volume integral because Bx, By are all force per unit volume. So, this can be written in this form, in the matrix form, and taking a variation of that, we get this in this form. Similarly, we can write the surface forces in this form, where Ts is the surface vector acting in the 3 coordinate direction, and similarly we can write in the damping in this form. While treating damping, there are different ways of damping. The damping could be frictional, damping could be based on material property, damping could be viscous. The most common type, which is mathematically easily tractable, is basically the viscous damping. So, we assume that the viscous damping force is given by this expression. So, we put this, which is directly proportional to some constant, which is called the damping constant, multiplied by the d dot. D dot is essentially the velocity vector. So, now we put all these things together, we get this whole thing in the in the Hamilton's theorem. Now, we simplify each one of them. Let us do that. So, before we do that, now we said that in finite element we assume the variation over each element. That is, the variation can be expressed in terms of the shape functions, which I talked about in the first slide, multiplied by the a n of t. In the a n of t is the elemental displacement vector of the element, which I call it as u e of t. For the sake of convenience, u e means e is the elemental vector, whereas u is the global vector. So, now I can get, because here d dot is n into u e, n e is only a spatial dependent. So, the time dependence comes from the displacement, and d double dot is essentially n into u e double dot, and delta d is equal to n into delta u e. So, basically now we put that into the first expression, which is the inertial expression coming from the kinetic energy. So, we can write this, and delta d transpose is nothing but delta u e transpose into n transpose multiplied by your d double dot is nothing but n into u e double dot. So, when I put this, I get this, and this quantity is called the mass matrix, and the way we do that is basically is the consistent mass matrix. Now, let us take the strain energy portion, which has the strain displacement matrix. So, strain displacement, we know epsilon x is equal to du by dx, etc. In matrix form it is given by here. Now, epsilon equal to b into d. So, now I know u, v, w are basically given by your the shape function relation. We substitute here u, v, w in this form. Then we can write epsilon equal to b into d, and delta epsilon is b into delta d. We substitute it into the strain energy expression here, that is basically coming from here. Then when we do that, we get this form, and this form b transpose c into b is basically the stiffness matrix, where c is the material matrix. We derive this material matrix for isotropic, orthotropic, or whatever the material conditions are in the structures. So, this can be written in this form mathematically. Similarly, we can write the body force delta d, using this expression here. We can write delta d transpose is delta u e transpose into n transpose, and multiplied by the body force vector, and this is the discretization of the body force. So, this basically converts the body force, which is distributed, into the concentrated force acting on the nodes. Similarly, we can do the surface force, and when we put all these things together, we get this equation, and here delta u e is the incremental displacement, which cannot go to 0 in this expression. So, the only thing that can go to 0 is the one within the bracket, and that is what is the governing equation, discretized form of the governing equation in the FEM. So, the mass matrix is completely got from the discretized portion, that is m transpose n transpose n. The damping is got here, n transpose n into eta, and k is b transpose c b integral. So, we have everything in the discretized form which we need to solve. If we are solving a static problem, we ignore this portion, we solve only k u equal to r. So, now let us introduce certain terminologies. Degree of freedom. What is degree of freedom? It is the number of independent motion a structure can support. Example, a rod can support only axial motion in the two directions, in the two nodes, and hence it has 2 degrees of freedom. It is a number of independent motions. For example, a beam can support both transverse motion and rotation. So, it is each node in a beam will have 2 degrees of freedom. A composite plate can support 3 translational motion, that is in 3 coordinate direction, and 2 rotation in plane direction. Hence, the plate node will have 5 degrees of freedom. If we need to add a twist about the axis, then we can add the 6th degree of freedom. To explain this a little bit, So, let us take a rod. So, rod can move only in this direction, it can move only in this direction. So, basically that means you have two, this is node 1, this is node 2. So, this can this is U1 and U2, correspondingly you have F1 and F2. So, it can support only 2 degrees of. So, this is a 2 DOF model. As I said earlier, a plate can I am sorry, a beam, this is a rod. So, this is a beam can bend. So, it can bend, it can undergo this bending, and this bending is caused by the rotation, that is the moment that is applied at the end. So, it can support the transverse displacement W at node 1, this is node 2, W1 and W2, and it can support theta 1 and theta 2. And corresponding to the W1, because everything will have a displacement dependent variable determination and a force variation, and what is cause and effect as we found in the variation principle. The W1 is caused by the shear force 1, W2 is caused by shear force 2, and theta 1 is caused by the moment 1 and moment 2. And as I said, if it is a composite beam, the midplane does not coincide with the neutral plane. That means there will be an additional component U, U1, U2, F1, F2. So, it is basically a combination of both rod and beam. So, each will have 3 degrees of freedom, and the matrix will be, this will have 3 degrees of freedom per node and 6 DOF per element. So, if it is a plate, we have plate. So, you would basically have, it can have the translation degrees of freedom U, W, V, then it can have the theta x, theta y, and you can also have a twist degree of freedom if there is a twisting angle to it. So, these are called the independent degrees of freedom that you have to be very, you should understand what is an independent degrees of freedom. So, every beam will have a degree of freedom that is defined by the motion that is the structure is undergoing. The other one is the continuity. So, as I said earlier, across the element boundary, all the displacement need to be continuous, that is a derivative should exist. For example, in the case of a rod or a plane stress element, it is necessary to have only displacement to be continuous. Such a continuity requirement is called C0 continuous element. That is, for example, if you have a rod, a series of rod element, and we isolate this is element 1 and element 2. So, the element 1, this will have 1 and 2, 3. So, 1, 2. So, the element, the displacement, the rod, the axial displacement at 2 due to element 1 should be equal to the axial displacement at 2 due to element 2. That is not at all an issue because it can be maintained. But if it is a beam, normally in beam the slope theta here is derived from dw by dx from the transverse displacement w. So, if it is a beam, then we need to see that the slope at 2 due to element 1 should also be continuous due to slope at 2 due to element 2. So, in the case of beam, we need both w and dw by dx to be continuous. So, there are two variables, the primary dependent variable and its derivative needs to be continuous. Such a continuity requirement is called the C1 continuous element. So, basically the C1 continuous element is a problem. It is not easy to satisfy, especially when we go from beam to some other higher elements. So, that is a problem with the beam. So, in order to avoid this, people introduce what is called the shear deformation, into the beam formulation, and such a beam theory is called the Timoshenko beam theory, and if it is introduced in plate, it is called the Mindlin plate theory. There theta in these beams, theta is not equal to dw by dx, and theta can be independently interpolated. So, then you need only w and theta to be continuous, so that you do not need the first order continuity, which is easier to solve. So, we can still build in the C1 C0 continuity in beam, provided we use Timoshenko beam theory. Now, let us come to the shape functions. So, as I said, I go back to equation 1 when we said that we approximate the dependent variable or the displacement within the element by a series shown by this equation, where a n of t is basically the what is called the shape functions, I am sorry, the degree of freedom or the nodal displacement, and phi n is the shape function. These are basically, this phi n are basically the one which satisfies the governing boundary conditions, or they are normally used by approximating this whole thing into a polynomial, which is dictated by the order of degrees of freedom. For example, if it is a rod problem, so for the rod problem we basically have the element has 2 degrees of freedom, x equal to 0 and x equal to L. So, if we want to approximate the variation within the element, we need to use polynomial, we need to have 2 constants, unknown constants into the variable that we are assuming. Why? Because it can support only 2 motions, that is x equal to 0 and x equal to L, that is u1 and u2. So, if we for this 2 unknowns, we need to have 2 constants. So, we take this equation u of x t equal to a naught plus a1 t into x. So, in this above expression, we know that the constants are here a naught and a1 are time dependent if we are talking about a dynamic problem, or it is simply a constant in the case of static problem. Now, we substitute that at x equal to 0 is equal to u1, because we start our axis here, this is x equal to 0, and u at x equal to L will be equal to u1, the above equation. Then we will write the u1 and u2 in terms of the unknown constants. So, that is given by, so now I can say u1 u2 equal to 1 1 0 L a naught and a1, and we invert this matrix, then we get a naught a1 equal to 1 by L, L 0 minus 1 u1 u2. Now, we substitute this back into our equation 1, and we can write and factorize all the u1 and u2 separately. Then we can write u of x equal to 1 minus x by L into u1 and x by L into u2. So, this x by L, 1 minus x by L and x by L are called the shape functions for the rod element. So, then we can write u of x t is sum of I equal to 1 to 2 n1 into u1 ni into ui, or you can be writing as n1 into matrix, this is n matrix and u1 u2, where n1 into are given by this. As I said, these are the shape functions for a rod element. So, what are the properties of the shape functions? If we go back, x equal to 0 is the left node where displacement is u1, and x equal to L is the right node, which is where the displacement is u2. And now suppose we substitute x equal to 0 here, that is at the left node, n1 will be equal to 1 and n2 will be 0. So, it takes the value of unity at node 1 where the displacement is has to be satisfied. So, at node 1 we need displacement to be u1. So, u2 should go to 0. So, that is why x equal to 0. At x equal to 0, the n2 goes to 0, n1 is 1. At x equal to L, n1 goes to 0 and n2 will be equal to 1. So, n1 takes the value of 1 at node 1 and 0 at node 2, and n2 takes the value of node value of 1 in node 2 and 0 at node 1. And let us evaluate the sum of the n1 plus n2, which is equal to 1. So, the sum of shape functions are always equal to 1. So, these are some of the properties of the shape function. It takes a value of unity at the value at the node where you are evaluating it, the coordinate, and all other places it is 0. We will do the same thing with beam element. As I said, the beam element has 2 degrees of freedom for node, which is W is the transverse displacement and theta is the rotation. Now we write, so now it has, so the minimum order that is needed here is it has to have 4 degrees of freedom are there. So with the assumed polynomial field, if we assume polynomial, should have at least 4 constants for determination of these 4 boundary conditions, the displacement boundary conditions. So that means minimum we need a cubic. So the higher order approximation that is required because of these 4 degrees of freedom will lead to a continuity requirement which is C1, mainly because, as I said earlier, both W and dW by dx have to be continuous at the inter-element boundary. So we take a cubic polynomial here. So what we do, we substitute at x equal to 0, W is equal to 0. So that is given here. So at x equal to 0, W1 you have W1, at x equal to L the 0 dW by dx is equal to theta 1, because the slope is derived from the displacement. At x equal to L the transverse displacement W2, and at x equal to L theta dW by dx will be equal to theta 2. When we substitute this, we can relate u with theta, and inverting it we get the unknown constants a0, a1, a2 can be related to the nodal displacement by this. And when we substitute this back into our original equation here for a0, a1, a2, a3, we can write W equal to n1, n2, n3, n4 of u. So, ni into ui, that is the standard form for all finite element formulation, and we get the following shape functions. So, a lot of mathematics has to be done, just it is a matrix inversion. Once you do that, we get this. So, let us look at this shape function. Does it satisfies the shape function properties? That is, we need that it takes a value of 1 at where it is evaluated. Suppose we substitute at x equal to 0, we expect that the n1 should go to value 1 and all others should go to 0. So, at x equal to 0, we clearly see n1 is 1 and n2, n3, n4 are all 0. If we substitute x equal to L, we see that everything. So, when this is x equal to L, we have 1 plus 3, 2, 3 minus 3 is 0, n2 will be 0, this will be 0, n3 will be 1 because it is the transverse displacement, that is 3 minus 2, and n4 will be equal to 0. Then what about the theta degrees of freedom? So, the n2 will not go to 0 when x equal to 0, because what we are looking at, n2 is the shape function for the dW by dx, that is the rotation which is got from W, and samely n4 which is got, it is the theta, it is the shape function for theta at node 2, that right node. So, we will find that the dn2 by dx, that is because W is derived from the theta is derived from the W, we need to take dn2 by dx and substitute at x equal to 0, you will see that this will be equal to 1 and this will be 0, and when x equal to L dW by dn2 by dx will basically this will be equal to 0 and this will be equal to 1. So, that is precisely what I have written here. These shape functions are essentially satisfies the properties of the function, and I have specifically said that n2, which corresponds shape function of the slope at node 1, does not take a value of unity at x equal to 0, even though it is evaluated at that node. Only dn2 by dx is equal to 0. And if you plot this, you see that the variation, it takes a n1 takes a value of 1 and 0 at 2, the slope dn2 by dx takes a value of 1 at node 1 and 0 elsewhere. This is n3, which is again corresponding to the transverse function, and this is the. So, this is how the shape functions vary. Now, let us go to a 2-dimensional element, and suppose we have a rectangular element of length 2a and width 2b, which has 4 nodes, and each node can take 2 degrees of freedom, that is u and v in 2 horizontal directions. So, it will have totally an 8 degree of freedom element. So, for 8, so we have 4 u degrees of freedom and 4 v degrees of freedom. That means, the polynomial is not only x, it is also y dependency is there. It will have x and y, and it should have 4 constants both in u and v. So, we take the form u of x y is equal to a naught plus a1 x plus a2 y plus a3 x y. Similarly, we have b naught plus b1 x, b2 y and b3 x. So, there are 8 constants corresponding to 8 degrees of freedom here. So, now we substitute the coordinates of the element. So, here the axis is exactly at the middle. So, we have a middle axis, this is x and y. So, this is corresponds to minus a, and this is plus a, and minus b and plus b. So, we substitute this equation into the assumed function here in this function, and we evaluate the coefficients. We can write a will be equal to this g inverse into u, where my u will be a vector u1 v1 u2 v2 to u4 v4. So, this is the vector of my u displacement. So, when I substitute this back into this relation and simplify, we can write u equal to n1 n2 n3 n4 into only u degrees of freedom, which will have u1 u2 u3 u4. This will have only u1 u2 u3 u4 transpose, and this will have only the vertical degrees of freedom, that is v1 v2 v3 v4. Okay. And each one can be given x minus a into y minus b by 4, x minus a into y plus b by 4, x plus a into y plus b by 4, x plus a into y minus b by 4. If you look at this carefully, let us substitute at x equal to minus a into b. Suppose we want u1, which is minus a into minus b, this will be equal to, this takes a value of, so this is basically equal to, I am sorry, this is 4ab, everywhere you have a 4ab here. So, when you substitute x equal to minus a into x y equal to minus b here, n1 takes a value of unity, whereas n2 will be 0 at y equal to minus b, this will be 0, this will be. And similarly, when we take the value of say u2 at minus a in b, so n2 takes a value of unity. So, and if you take the sum of n1 plus n2 plus n3 plus n4, it will always be equal to 1. So, all these properties are followed, and if this is not followed, then they are not called the shape functions. Now, for the triangular element, how do we do it? So, now let us look at it is very important element, but very inconvenient to generate the shape function by the procedure we adopted before, even though it can be done. So, here we take a slightly different approach, where we will not use the conventional coordinates, which is given by you have x1 y1, x2 y2 and x3 y3. What we will do here is, we will take any point for which we require a coordinate. We split up this into 3 areas, we call them a1, a2, a3. Okay. And if I want the area can be got from the coordinates. If A is the total area of the triangle, they can be got from the expression given here, which is the determinant of this, where x1, x2, x3 are the rectangular coordinates of the original element. So, now we will define the area coordinate for this problem, or the point P is, it is located by L1, L2, L3, where L1, L2 is the sub area A1 by A. So, if you look at it, the sub area A1 divided by A is the L1. L1 is the one where the opposite node is the node 1. Similarly, we take L2, which is the sub area A2 by A, L3 is A3 by A. The position of the point is thus given by these coordinates, which are normally referred to as area coordinates and are not independent, and they satisfy the relation L1, L2 plus L3. So, the moment you solve that, it is similar to our shape function, sum of shape functions satisfying the equation n1 plus n2 plus n3 equal to 1, where the coordinate x can also be related. I am not going into the derivations of this, through this relation L1 x1, L2 x2, L3 x3, and these L's are derived. So, from this we can derive the expression between L and the coordinates, that is A1 will be, here we say Li will be Ai Bi x plus Ciy by 2a, where A, B, C's are given by in terms of the coordinates. So, you can get L1 will be A1 B1 C1, L2 will be A2 B2 C2, and from these are all cyclic permutations which we can get. So, basically the above equation requires to be used, we will use this when we want to find the derivatives, because in most of our B matrix we need dn by dx with respect to x. When we have the area coordinates L, we need to use this expression to get the derivative with respect to x. So, that is why we need these relations. So, this is more convenient to do that. So, now we can write these shape functions for the triangle as u equal to n1 u1 n2 u2 n3 u3, where n1 is nothing but your area coordinates L1, L2 and L3. So, here these shape functions also follow the normal rules, that is, it takes a value of a where L1 is equal to 1 at the node 1 and 0 elsewhere, and L2 and L3 is 0 at node 1. So, in order to fix this, we can go back here. So, at this point L1 is equal to 1, at here L1 equal to 0, and if you come here L2 is equal to 1 and L2 equal to 0. If you come here L3 equal to 1, L3 equal to 1 and L3 equal to 0. So, basically here when you say here, in this point L3 is 0, L2 is 0, but L1 is 1. If you look at here, L2 is 1, but L1 and L3 are 0. So, it satisfies the property of the shape function, and at the same time it elegantly we can able to formulate the element in a more convenient manner. The conventional method will give us a lot of problems. So, what are the rules for choosing the interpolating functions? The assumed solution should be able to capture the rigid body motion, and this can be made sure by retaining the constant part of the assumed solution. That is basically what we are saying here is, so if you have a function u equal to a naught plus a1x plus a1 x square, a2 x square, etc., the constant part make sure that the rigid body motion can be present in the assumed function, which is absolutely necessary for convergence of the solution. The assumed solution must be able to retain the constant state of strain as the mesh is refined, and this can be assured by retaining the linear part, that is the linear part a1x in the interpolating function. This is absolutely necessary. These are some of the rules that we need to follow. Most second order systems, that is the second order system is where the differential equation is order 2 requires only C0 continuity. So, you want only displacement to be continuous. We explained this, which can be easily met in most finite element formulation. However, for higher order systems such as the Bernoulli-Euler beam, where the elementary beam, where or the plates where the slopes are derived from displacement, theta is w dw by dx, we need to see that both w and dw by dx are continuous across the element, which are extremely difficult to satisfy in the inter-element country. So, in such situations what we do is we introduce shear deformation, as I said earlier, and the Bernoulli beam is converted into Timoshenko beam, where w is not derived from the theta is not derived from the slope, that is theta is not equal to dw by dx, where now we need to have only w and theta continuity, that is we go back to C0 continuity. Now, if you look at it, if the beam is very thick, shear deformation is very predominant, we can use Timoshenko theory. Suppose the beam is very thin, there is no shear deformation, you cannot make a C1 continuous to become C0 just by using relaxing this. So, in which case the displacement predicted would be many orders smaller than the correct displacements, and such a problem is called the shear locking problem. So, we have to be very careful while actually migrating from C0 to C1 by using different beam theories. The order of assumed polynomial is dictated by the highest order of the derivative appearing in the energy functional. That is, the assumed polynomial should be at least one order higher than what is appearing in the energy function. To understand this, now if you take a beam, you have u will be equal to 0 to L EI d square w by dx square whole square to dx. And suppose you assume a linear polynomial, which you cannot do anyway. If you assume it, then the energy will go to 0, because d squared by d square w by dx square will not exist. And suppose you use a quadratic polynomial, then d squared w by dx square will only be a constant. So, we at least make sure that in the case of a beam, we need to have something which is where the order is one more higher order should be there. So, what we need to choose is choose a polynomial where d cube w by dx cube exists. So, basically that is what is required here. So, in summary, what are we doing here? For all the elements, we can express the displacements in terms of shape functions and nodal displacement, which are given by u equal to un into, which is given here, un into un, ui into ni, ni into ui, and the spatial discretion will be used in the weak form of the governing equation, substituted there, and then we formulate the stiffness and mass matrices. Then these matrices will then be used, assembled, solved for getting the solution of the structure. This is in summary about how the finite element process takes place. Now, let us look at some of the element formulation. This is a rod element formulation where you have n1 and n2 given by here, where n1 is equal to 1 minus x by L and x by L. We use these shape functions. Then we know this is the stiffness matrix, we have derived this. So, we put this into this system. So, when the strain, the B is the strain display, only relevant strain is epsilon xx. So, only you will have C present here, then we put the C back here. So, once we use this, we can actually get the strain displacement matrices, and the C matrix will contain only E, the Young's modulus. We substitute all this thing into this equation, replace C by E. Once we do that, we get this equation, and we put this back here, and this is the stiffness matrix for a rod. We see that it is symmetric, and it is a function of the material property E, sectional property A, and length. Similarly, we can do the beam element formulation. where we have the displacement relation between the the axial displacement is given by theta times slope. So, basically when the beam bends we have, so this is the mid plane. So, we draw this and this is the axial displacement which is the theta. So, that is the z times theta is nothing but the axial displacement, and this one, and using the strain displacement relation we find that this is second order strains, and we have the normal strains in the y direction. If this is x and this is z, so the sigma z in this direction is 0, the shear strain is 0. So, only relevant material matrix here is again E. Here we plug this back into this equation and derive the strain displacement matrix, which is du by dx, which is given by there, and when we substitute for u we get this is a second order matrix, and we substitute back into the governing differential equation and integrate between 0 to L, we get this is the governing equation. So, basically we have done this, and now in summary what we have understood here is we have developed the FE equations, outlined the procedures for finding out the shape functions, and also derived some of the elements that can be directly go into our analysis like rods and beams, and we also discussed few issues concerning the choice of the interpolating functions, etc. Thank you.